So the topic of discussion today is the applications of the agreement problem, because as far as the algorithms which are used for solving the agreement problems, it finds many applications in which the different processors have to reach on an agreement regarding their values in presence of the faulty processors. So we have basically the application has been divided into two parts. The first application is related with the clock synchronization, and second application is related with the atomic commit in the case of distributed database system. So first of all, we will be discussing about fault-tolerant clock synchronization application, and we have two algorithms in that clock synchronization process. One is interactive convergence algorithm, and second one is the interactive consistency algorithm. Interactive convergence algorithm is a kind of an algorithm in which, as far as the synchronization of the all the processors are concerned, they communicate with each other by giving the values to the other processors, and ultimately they are going to converge and decide and agree on a common value. And interactive consistency algorithm, and that is why the name has been given, convergence and the consistency. And in the consistency algorithm, all the processors tries to find out the values which has been exchanged in between the different processors, so that the values should be consistent enough. So first one is the convergence and second one is the consistency. But before going to that algorithm in detail, first of all, let us find that what is actually fault-tolerant clock synchronization case. Now, as in distributed systems are concerned, it is very important that all the sites or all the processes which are working together for achieving the common goal, they all should maintain the physical clocks. Since every process is maintaining its physical clock, so it is also necessary that it should be synchronized with one another. Every clock which is available at the different processes, it should be synchronized. But we know that whatever physical clocks are available at the different processes, there is a problem which is called the drift problem, and because of that drift problem, even though they are synchronized initially, they are due to drift problem, there may be possibility that the clocks of the different processors are going to vary. So what they have suggested that it should be resynchronized periodically. So once after a few times it should be resynchronized. Once it is synchronized and then process is going on, everybody is doing its own job, it's working, but after few times it should be resynchronized. So this resynchronization is again a kind of a process in which all the other processes which are available in the system must work together on the same clock time. But this periodic synchronization, it is going to become a difficult job if the Byzantine failure is allowed. Because in the case of Byzantine failure, if there is a faulty processor and that faulty processor is going to report the different clock values to the different processors. So in that particular case, the resynchronization becomes very difficult. So whenever we do the synchronization process, as far as the clocks of the different processes are concerned, we have to make certain assumptions, and based on that assumption, the solution of that can be found. So of course, we will be applying some algorithm which is used for the agreement problem in making the synchronization possible. That is why one of the application is the fault-tolerant clock synchronization. So the synchronization, which is based on the different assumption. The first assumption is that all the clocks are synchronized initially the same value approximately. All the clocks are initially synchronized to approximately the same value. Now the second assumption is a non-faulty processor's clock run at approximately the correct rate. So whenever we talk about the correct rate means that 1 second of clock time is per second of the real time. So correct rate means whatever is the real time per second, the same is 1 second of the clock time. So, and there is no assumption which is made for the faulty processor. This is all the assumption which are made for the non-faulty processors. The third assumption is that a non-faulty process can read the clock value of another non-faulty processor with at most a small error. Because whenever a process is going to read the clock value of the other process, it may be possible that there is a lag of time. So whenever a non-faulty process is going to read the clock value of the other non-faulty processes, so there may be a possibility that there will be a small error which is designated by epsilon. Now, whatever clock synchronization algorithm which is made for synchronizing the clocks of all the processes which is available in the distributed system, they must satisfy the two conditions. The first condition is that at any time the values of the clock of all non-faulty process must be approximately equal. Whenever we talk about approximately equal, there may be some certain drift, there may be certain difference, but this difference should be very small amount of the time, very small. If there is an error, the error must be very small. It can be represented by epsilon. So at any time, the values of the clock of all the non-faulty processes must be approximately equal. And there is a small bound, whatever we're talking about, the small error, there is a small bound on the amount by which the clock of a non-faulty processor is changed during each resynchronization. So whenever we are doing resynchronization, the amount by which it is going to change the clock value after resynchronization, it must be very small in case. So the meaning of this second assumption, the second condition, it is going to imply that the resynchronization does not cause a clock value to jump arbitrarily far. ऐसा नहीं है कि बहुत ज्यादा difference होना चाहिए, हो गया होगा. The resynchronization does not cause the clock value to jump arbitrarily far. Thereby, it is going to prevent the clock rate from being too far from the real time. Whatever is the real time, उससे बहुत far नहीं होना चाहिए. It should be close to the real time. So, for obtaining this condition to be satisfied, we have two algorithms, and these algorithms, as I mentioned earlier, the first one is the interactive convergence algorithm, and second one is the interactive consistency algorithm, which are fault tolerant to the Byzantine failures. So, as far as the interactive convergence algorithm is concerned, it has been given its name because it causes all the non-faulty processes to converge at a common value. And this interactive consistency algorithm the name has been given just because all non-faulty processors obtain the mutual consistency view of all the clocks. So we will be discussing one by one. The first one is the interactive convergence algorithm. Now, this algorithm assumes that the clocks are initially synchronized and they are resynchronized many times so that two non-faulty clocks never differ by more than delta. The delta is a small error. So assuming that all the clocks are initially synchronized and then they are resynchronized such that in such a manner they are resynchronized so that the clocks of the two non-faulty processes never differs in the value more than the delta, where delta is a small error which has been considered in this particular case. Now, what is that algorithm says? The algorithm says that each process reads the value of other process's clock and sets its clock value to the average of these values. So it means the process is going to read the other process's clock and it is going to set its value, its new value, by the average of the value which it is going to find. Now, if the clock value differs from its own clock, means after taking the average, if the value is going to differ from its own clock more than delta, because delta is the permitted error, if it is more than delta, then it replaces that value by its own clock value when taking an average. So meaning thereby whatever average we have taken, if the average value is going to drift more than delta from its own clock value, then what we do, we take the own clock value and the average value and then taking the average and replacing the clock value by that. So this algorithm seems to be very simple algorithm because we have the process is going to read other processes clock and taking the average value. If the average value is not differing more than delta, then it is going to replace that. Otherwise, if it is more than delta, then it is going to replace its own clock value when taking the average. So of course it is a simple algorithm, but the problem with this algorithm is that if there is a presence of faulty clocks, faulty processes, which is going to report different values to the different processes, that kind of problem is called two-phased clocks, because the faulty processes are going to report one process to the different clock value, another process to the different clock value. So in that particular case, this algorithm is going to face the difficulty in taking care of the two-phase clock problem. But the ultimate aim of doing this synchronization process is that we want to put the things in the desired degree of resynchronization, meaning thereby we have a permissible limit, and within that limit we try to resynchronize. And in this algorithm, two assumptions have been made. The first one is all the processes execute the algorithm instantaneously at exactly the same time, meaning thereby whenever process is going to read, whether it is going to update, whenever it is going to resynchronize, whatever is being done, all the processes are going to execute instantaneously. The error in the reading another process clock is supposed to be zero. These two assumptions, because it may be possible that whenever it is going to read the other process's clock, then there may be a possibility of error. And if there is an error, it is considered to be zero. So with these two assumptions, it may be possible that the process may not execute algorithm instantaneously, because it is not possible for all the processes to execute the algorithm instantaneously. It may read other processes clock at different times instance. It may be possible, which can be overcome by computing the average of the difference in the clock value rather than the absolute value. So instead of taking the absolute value, what we do, we take the average of the difference in the clock value and then incrementing its own clock by the average increment. So whatever difference has been come, it is being added into the its own clock value to update its clock. So in this way, all the processes are going to converge on a common value by resynchronizing and adopting this algorithm to work together. So this is about the interactive convergence algorithm. The second one is interactive consistency algorithm. So besides in this interactive consistency algorithm, two improvements have been made in comparison to the interactive convergence algorithm. The first improvement is made, that is, instead of taking the mean value or the average value, we are calculating the median value. And by using a sophisticated technique, it is going to avoid the problem which is called the two-phase clock problem, which arises just because of the presence of the faulty processes, which is going to give different information to the different processes. So how this interactive consistency algorithm used to work? Two processes will compute approximately the same median if they obtain approximately the same set of clock values for the other processes. So instead of mean value or the average value, we are calculating median. So the first assumption is two processes will compute approximately the same median if they obtain approximately the same set of clock values from the other processes. So whenever we are going to impose the condition, there are first applied condition. The first applied condition for interactive consistency algorithm is that the first condition is any two process obtain approximately the same value for a process P clock. कोई एक process P है, तो बाकी दो और process हैं. So any two process are going to obtain approximately same value for the process P. Whatever is the clock value of the process P, any two more processes, suppose A and B, they are going to obtain approximately the same value of the P's clock, even if the process P is a faulty, even though the two processes are going to obtain the same value of the P's clock. Now, not only should all processes compute the same value, but their values should be close to the clock value of the non-faulty processes. So the applied condition, second applied condition is, if Q is a non-faulty process, then every non-faulty process obtains approximately the correct value of the process Q's clock. Now, there is a difference between the clock value and the correct value. This correct value stands for the real-time value. So if Q is a non-faulty process, then every non-faulty process obtains approximately the correct value of the process Q's clock. Whatever is the value of the Q's clock, it is to be obtained in the form of a correct value by all the rest non-faulty processes. And by doing this, if the majority of the process are non-faulty, the median of all the clock's value is either approximately equal to the good clock's value, or it lies between the values of the two good clocks. So since we are taking the median, so ultimately whatever we are getting, the majority of the non-faulty processes are going to obtain approximately equal to the value they are going to obtain is approximately equal to the good clock's value, or it is going to obtain the value which is lying in between the two good clocks. Now, how this algorithm works. So as far as this interactive consistency algorithm for the clock synchronization, it works in this particular manner. First, all the processes execute an algorithm for an interactive consistency problem to collect the values of the clock of the other processes if they are going to satisfy the condition number 1, that is C1, and the condition number 2, that is C2. Now, the second thing is that all the processes, after collecting the clock values of the other processor, after satisfying the condition C1 and C2, every processor will be using the median of the collected values to compute its own clock values. So first of all, it has to collect the clock values from the other processors with the condition C1 and C2, where C1 says that the processes are going to obtain the same value of the process P, whether it is faulty or non-faulty. And second condition is, if the one process is a non-faulty process, then every rest of the non-faulty processes obtains approximately the correct value, whatever is the value of that Q process, it is going to obtain the same value. So the algorithm says that all the processes collect the clock value of other processes which satisfies the condition C1 and C2. And second is every process will be using, since once it is going to receive the clock value of other processes, it is going to calculate the mean of the collected value to compute its new clock value. Now, as far as the first step is concerned, the first step can be executed. How we execute the first step by applying the agreement problem algorithm. So the first step can be executed by using the every processes independently run the oral message protocol, which we have studied in the last one. So to run the oral message protocol and for the Byzantine problem, where a process sends a copy of its clock to every process as its initial value. So the first step can be obtained by applying the oral message protocol, which is used for the Byzantine problem, by sending its own clock value, the copy of its own clock value, to every process as its initial value. Now, when the algorithm OMM stops, means the oral message protocol with M has stopped, where M is the number of faulty processes. So when this algorithm is going to stop after making the convergence, because first of all, the source process will be sending its clock value. Whenever it is being received by the rest of the processes will also going to exchange the clock values which they have received from the source value. So, and while exchanging these values which they have received from the source, a time will come when it is going to stop. This algorithm is going to stop. So once this algorithm is going to stop at every process will have the clock values of all other processes, and this is going to satisfy the condition C1 and C2. And once the condition C1 and C2 has been satisfied, and every process has received the clock values of the other processes, at this particular time, every process will going to compute the median of the values and set its clock with that particular median. So this is the interactive consistency algorithm. Of course, in case of oral message protocol, what we have seen that we were taking the different processes are going to agree on a common value, and the common value, after exchanging of the messages or the values from one process to another process, they are going to take the majority of that value and going on the consensus that value will be the final value. But in this particular case, after receiving the clock values from all the processes, they are going to compute, all the processes are going to compute the median of these values, and then by whatever value they are getting after calculating the median, they are going to set its clock by that median value. So these are the two algorithms which is helping to solve the fault-tolerant clock synchronization. Now the second application is the atomic commit in the distributed database system. We know what is the atomic commit in the distributed database, because what happens in the distributed database system, that it has to agree, the distributed database must have to agree whether it is going to commit or it is going to abort a particular transaction. So what happens in the first phase of the atomic commit, what happens? Site is going to execute their part of the distributed transaction and broadcast its decision that whether it is going to commit the transaction or it is going to abort the transaction to all the sites. And in the second phase, whenever this information has been received by the receiving sites in the first phase, then they are going to decide whether they are going to decide that whether they are going for commit or they are going to abort as the part of the distributed transaction. So what happens that every site is receiving an identical response from all the other sites, and they will reach a particular decision whether they are going for commit or they are going to abort. But there is a problem that it may be possible that some of the sites, some of the processes may be behaving bad, may be behaving faulty, and they can send a conflicting response to the rest of the sites, and thus causing a conflicting decision. So whenever there is a conflicting decision, so in this particular situation, to solve this particular problem, we can use the algorithm which is used for the Byzantine agreement, and which is going to ensure that all the non-faulty processes to reach on a common consensus, on a common decision about the distributed transaction, whether they are going to commit or not. And how it works, the common decision, how they will be coming onto the common decision for the distributed transaction, whether they are going to commit or they are going to abort. So in the first phase, what happens if you apply the Byzantine agreement solution? So the first phase is that site, after a site has made a decision, it starts its Byzantine agreement, whatever way the Byzantine agreement is being done. And once it is going to do that, in the second phase, the processors determine a common decision based on the agreed vector or values. So again, the source will be sending its value, and once it is being received by the rest of the processes, they will be exchanging the value. If there are faulty processes, then they will be relaying the different values, but they ultimately all the processes are going to maintain a certain vector, and based on that values which is available in the vector, they are going to take the majority of the value, and after taking the majority of value, they are going to agree on the vector of that value. So this Byzantine algorithm or Byzantine agreement can be very much helpful in the doing the atomic commit about the transactions which is being done in the distributed database.